Hey everyone, today I will be talking about windstorms. However, due to the large scope of information, I will specifically be talking about downslope windstorms, a type of windstorm, which you guys know obviously occur in Boulder, Colorado, and are referred to as a Chinook. First, let's define what a windstorm is according to MedEd at UCAR. Windstorms are classified as high wind events not associated with convective events, coupled with either sustained wind speeds of 40 miles per hour or greater lasting for 1 hour or longer, and or winds of 58 miles per hour or greater for any duration. Although the processes that create this meteorological event are unique from that of other windstorms, there are still many similarities. Let's define what a downslope windstorm is. The definition of downslope windstorm is a very strong, usually gusty, and occasionally violent wind that blows down the lee slope of a mountain range, often reaching its peak strength near the foot of the mountains and weakening rapidly farther away from the mountains. They are prevalent synoptic scale weather phenomena that exist worldwide. In general, downslope windstorms are either foons or boras. Foon winds are classified as warm, dry, gusty downslope winds found along mountain ranges throughout the world. Chinook, derived from the Arapaho Indian word meaning snow eater, is the name given to the foon in western North America, especially on the plains to the lee or eastern side of the Rocky Mountains, in the United States and Canada. Their warmth results from adiabatic compression as winds descend leeward slopes. Bora winds are classified as cold downslope windstorms that result from a deep and very cold upstream air mass that spills over the barrier and displaces a warmer air mass. Although the air is heated adiabatically, as with foons, the original substantially colder air temperatures never exceed even the warmest surrounding air temperatures. In the morning of October 25, 1997, this destructive windstorm flattened 13,000 acres of old-growth forest in the Colorado Rocky Mountains. Easterly wind gusts in excess of 100 knots were observed just west of the mountain crest. Trees were stacked as high as 10 meters in some locations. The blowdown affected an area several miles wide and 20 miles long. According to the U.S. Forest Service, this was the largest known forest blowdown ever recorded in the Rocky Mountains. As you guys know, the westerly wind is anticipated, and easterly winds in this event rarely occur and appear to have contributed to the severity of the damage. The trees which had grown to withstand westerly winds. Another case is on January 17, 1982, in Boulder, Colorado. On this day, they experienced one of the most notable Chinooks. As the windstorm unleashed its fury, there was a 137 mile per hour gust at NCAR, 20 gusts above 125 miles per hour in 45 minutes, at least 15 injuries, and 40% of the buildings in Boulder were damaged. That contributed to the total $20 million in damage. Despite the aggregate loss, fortunately, no fatalities were reported on this day. So now I will discuss what the basic physical processes to create this event are. The basic physical process that must be present in order for a severe downslope windstorm to arise can sometimes be associated with mountain wave systems in which a strong, conducive downslope windstorm occurs. The necessary components for such a case are typically composed of strong cross-barrier flow, waves breaking aloft, and an inversion, which creates a stable atmosphere near the barrier top. Mountain wave systems occur when a strong wind flow perpendicular to a primary ridge line in a stable atmosphere initiates the development of mountain waves. In this picture, you can see that a westerly wind is present. These stationary waves are analogous to the standing waves seen in many river rapids. Like the water that moves over the standing wave, the air moves through the stationary wave. As we've already discussed in class, the formation of cap clouds can occur and indicate likely wave activity downstream. They often appear along the mountain ridge as air is forced up the windward side. If the flow is sufficiently humid, the moisture will condense into a cloud bank that follows mountain contours. Quite often, heavy orographic precipitation occurs on the upwind side of the barrier, particularly for barriers located near the sea. As the flow descends in the lee of the mountain ridge, the cloud evaporates. Viewed from downstream, cap clouds frequently appear as a wall of clouds hanging over the ridge top. It is important to remember that while cap clouds indicate likely wave activity, their absence does not mean that waves are absent. Under drier conditions, waves may easily be present without cap clouds. Due to the existence of a stable atmosphere for these stationary waves to form, the air will experience buoyancy oscillation as it attempts to find its equilibrium level after crossing the ridge top. It will move downward along the lee slopes, then oscillate in a series of waves as it moves downstream. The diagram represents a parcel of air in regards to a generally linear equilibrium level. As the cold air is being heated on the lee slope by adiabatic compression, it becomes warmer, therefore less dense than the equilibrium level, and consequently rises above this level. As the parcel overshoots its equilibrium level, it is now colder, therefore more dense in its environment, and is then driven by negative buoyancy. Like a mass between two springs, the parcel oscillates around its equilibrium level until frictional drag and turbulence gradually cause the oscillation to weaken. Essentially, these vertically propagating waves may break if they obtain sufficient amplitude, usually resulting in extreme turbulence. In this diagram, you can see the breaking region if the waves have sufficient amplitude. Lee waves, however, can occur when the wave energy does not propagate vertically because of low stability or strong wind. Instead, they propagate more horizontally over a longer distance. Sometimes they are called lee wave trains. Lenticular clouds form near the crests of mountain waves. As air ascends and cools, moisture condenses, forming the cloud. As that air descends in the lee of the wave crest, the cloud evaporates. Because air flows through the cloud while the cloud itself is relatively stationary, many people refer to these clouds as standing lenticulars. So here's an actual picture of lenticular, rotor, and cap clouds. In order for downslope windstorms to strengthen in intensity, two common requirements are the presence of an inversion or critical layer. The sufficient presence of either one can contribute to the development of and/or strengthening of a downslope windstorm. The downslope winds can approximately be 2 to 3 times the upwind speed at ridgetop height. Mountain waves cannot form in a stable atmosphere as previously stated, so an inversion may act as a critical layer. The vertically propagating waves cannot continue upward into an unstable atmosphere, therefore it is redirected and concentrated downward on the lee slope. A critical layer happens when wind shear causes zero cross-barrier flow aloft or flow reversal aloft, while still allowing for mountain wave development. The critical layer acts as a layer in which the vertically propagating waves cannot continue upward, as seen with lee waves, but instead are deflected off the critical layer itself, which consequently accelerates the flow down the lee slope. As you can see, the downslope windstorms often end at the jump region, although more moderate turbulence can exist downstream. The jump region is an extremely turbulent area that can extend up to 10,000 feet. Rotors are part of a low-level turbulent zone that often forms in association with a mountain wave system. They can be found after the jump region. Rotors are called horizontal roll vortices because they form a complete rotational pattern, with the axis of rotation parallel to the ground. Rotor axes typically occur at an altitude equal to or below mountaintop level and within 20 nautical miles of the ridgeline. Smaller scale rotations embedded within the lower level turbulent zone can cause rolling that exceeds an aircraft's ability to stay level. Similarly to how cap clouds can be identified if there is sufficient moisture that is able to form a cloud, rotation locations can often be identified if sufficient moisture is available to form an associated rotor cloud. Rotor clouds are found near the top of the rotor circulation and under high lenticular clouds. Immediately above the rotor cloud, smooth, wavy air is likely. The rotor cloud can often look harmless, but it does contain strong turbulence and should be avoided by pilots. In general, the life of a downslope windstorm continues to thrive unless one of the necessary conditions discussed either diminishes to an inadequate sufficiency or entirely dissipates.